Hi everybody, today I want to talk about surface plasmons. First, I give a brief history about them, and then I drive some equations and some features for them. So the first documented observation of plasmons dates back to 1902 when Wood illuminated a metallic diffraction grating with light and noticed narrow dark bands in the spectrum of the diffracted light. It was in late 1950s Ritchie first started talking about them theoretically, and since then, surface plasmon has been an interesting topic for scientists, physicists, and engineers. I want to start off with a definition. Surface plasmons are traveling electromagnetic wave oscillation of electrons that can be excited in the surface of certain metals with right properties. So next step, I want to use my knowledge in electromagnetic theory to uh, derive them or describe them mathematically. So I just want to use the surface plasmons or surface waves. So it means that there is a wave going on a surface. So it means that I have a boundary. So this is a boundary, epsilon 1, epsilon 2, mu 0 and mu 0 because they're not magnetic. It is a really simple case. I need a coordinate system x, z. So this the boundary is here, medium 1, medium 2, and so based on the surface wave, if any surface wave could be occurring in this configuration, it would be in x direction. So it means that we have or it has attenuation or decaying along the z-axis. So I just want to put my description into equations, but before that I want to just assume that I have Tm polarization, and later I will talk about Te as well. So for Tm, since we have two media, so Z positive, Z negative, so I talk about H1. So since it's Tm, so it's gonna be along y-axis H1 E I K X X minus omega T and E minus alpha Z. So notice for the sign of this guy, this is negative because Z is positive, so this term represent the decaying in along the Z-axis, and this is the section, or this is the part showing wave going in this direction. So H2 the same, I had H2 E I to the KXX. I use the same KX as this guy because based on boundary condition I know that the wave constant stay unchanged along x direction. And plus alpha 2z because the z is negative, and I know that alpha 1 and alpha 2 both are positive. I can find the associated E as well easily. So E is 1 over I omega epsilon 1 minus alpha along x-axis minus I kx along the axis, and the exact same of these, which I'm not gonna write down. E2 is 1 over I omega epsilon 2 alpha 2 x hat minus I kx z hat h2 the same. So to relate these two equation together and these two together, I have to use boundary conditions. So the boundary condition state that tangential component of E and H must be continuous. So by writing that, H1 equals to H2, and this is a really important equation because minus alpha 2 equals to alpha 1 over all 2. So from this I can deduce that epsilon r epsilon 2 negative. So it means that one of epsilon 1 or epsilon 2 must be negative. So from the dispersion concept, we know negative epsilon happens to metals at some frequency. But this is some metals. For some metals, they don't support surface plasmons. In other words, having negative epsilon doesn't necessarily mean that every metal or every metallic surface can support surface plasmons, because metals have like epsilon, epsilon r, and epsilon imaginary, real and imaginary part. So we usually assume that this equation holds, and we know that imaginary part is associated with losses. So if the metal has a big loss, and this is comparable, imaginary part is comparable to real part, so they don't support surface plasmons. So I just want to talk about, or I want to have an intuition about why conductors support surface plasmons. So metals have a sea of free electrons, and when an external field is applied, the electrons are pushed into new positions. So the electrons tends to flow along the surface of the metals, as you know. So if this is conductor, so we have E along this direction. So it's gonna be negative, 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 and these are the ions. So the induced charges on the surface create their own induced electric field that tends to cancel the applied electric field in the conductor. So roughly analogous arguments may be made concerning the electric field of a light wave. The electric field of a visible light oscillates so rapidly, roughly 10 to the 15 cycles per second. So this field sets the electrons in the metal oscillating mostly near the surface. Generally, these electrons just vibrate back and forth, but under the right conditions, the light wave can excite a wave of electrons. This electron wave produces its own electromagnetic wave. So this plasmonic wave is confined to a very small region near the surface of the metal, because of the free electrons mainly are focused on the surface. So in the next section, I want to talk about the Helmholtz equations, and I want to drive the wave constant for um, plasmons. So this is the Helmholtz equation. So I can easily write this down by doing this. Two, and for this is exactly the same. Plus alpha 2 is going to be 2. So if I solve these two equations for alpha 1 and alpha 2, and I find alpha 1 over alpha 2 squared, based on the equations offered in this part, I can easily relate alpha 1 and alpha 2 this fraction to this fraction, epsilon 1 and epsilon 2. So by doing that, and by solving the equation for kx, I can find the kx in terms of epsilons. So since epsilon R2 or epsilon R1 is negative, so this means that for a given frequency, the wave number of a surface plasmon is always larger than that of a light wave in vacuum. So in other words, because of this relation, 2 pi over lambda, so it means that in other words, a surface plasmon has a shorter wavelength than that of a light moving in free space or moving in a medium. Let's just consider this phenomena in terms of energy and momentum. So I just want to talk about the particle side of the wave, or the particle side of the light. So for a quantum particle of light called photon propagating in vacuum, the associated energy is E equals to h bar omega, which h is Planck's constant and omega is temporal frequency. And for the momentum, I can easily write down h bar k, which k is the wave number, and I can write down momentum and speed of light. So based on the equations, a surface plasmon always has a larger momentum than a photon. So this is not a good news. So it means that for a photon to convert to a surface plasmon, additional momentum must be provided. So in other words, light shining on a metal or a plane wave shining on a metal surface will not excite plasmons. So in order to solve this problem, we have couple of solutions, but one of the best and one of the easiest one is to use a prism that we saw in class. But how a prism can cause or can excite a surface or surface waves. So when light travels in a material with a refractive index larger than 1, so wave number is going to change because k equals to omega mu epsilon. So, or I can write down k naught n. So k is increasing. So now, if this light wave experiences a total internal reflection on the inner surface of the material, it produces an evanescence wave outside that has a horizontal momentum greater than k. So if the let me just draw. So if I have a metal here, tin, and I just make it big enough, and we have a light coming in, and we have a out. So this is the evanescent region. So it means that if the evanescent wave is brought close enough to the metal surface that supports plasmons, it excites them directly. In other words, by using internal reflection, the whole internal reflection and prism, we are just increasing the kx in this direction because they need additional kx to excite surface plasmons. So this is the main reason that we use prism in class 2. So I hope this video helps you for the finals, and thank you for being with me.